Greetings everyone, and today we are going to discuss about hybridization. The concept of hybridization was first given by Pauli in order to find the valency of certain elements, including carbon, beryllium, and boron, which were not described by electronic configuration provided by Hunds. Pauli provided this explanation. In this explanation, the word hybridization, it means up of mixing up of two different two different orbitals, mixing up of two different orbitals of two different shape, sizes, and energy. In this case, there can be orbitals such as s orbital, p orbital, s orbital, p x orbital, p y orbital, p z orbital. In that case, we can take the example of two orbitals. For suppose as there is, for suppose this is s orbital, which is having one electron, which is having positive charge. Suppose this is s orbital. On the other hand side, there is a p orbital, dumbbell shaped p orbital. Now, when both of these orbitals are having different shape, this is spherical, this is dumbbell having different energy. This is low energy, this is high energy. Apart from which, having different size are combined together in order to form a single orbital, which is to be known as sp orbital which is known as sp orbital. In this case, sp orbital will combine in such a manner that the positive side of s orbital will combine with the positive lobe of p orbital, due to which it will form a longer due to which it will form a bigger positive lobe of the sp orbital, which will be bigger in size, while a smaller s sp orbitals smaller negative lobe. In that case, that is formed due to two positive charges and one negative charge. Now, how is this reaction occurring, and how can we do it in actual? In order to combine both of these orbitals, s and p orbitals, we require heat of reaction. What does this mean? This means that here, as we know, that for suppose let us take the example of carbon. Carbon having its valency as 1s, 2s, 1s2, 2s2, then 2px1, 2py1, and 2pz0. In this case here, 1s2, 1s2, 2s2 are completely filled. When carbon is provided heat, when carbon is provided heat of reaction, when it undergoes a reaction, and form covalent bonds. For suppose carbon reacts with, for suppose it reacts with hydrogen. So suppose carbon reacts with hydrogen, then the heat of reaction which is obtained during now the heat of reaction which is provided to the carbon in order to do this reaction will cause the carbon to gain the heat of reaction, and as the carbon will gain the heat of reaction, the 1s orbital being part of the k shell 1s orbital being part of the k shell 1s orbital being part of the k shell will remain aside, while we know that 1s is a part of k shell and 2s, 2px, 2py, 2pz are parts of the L shell. In that case, we cannot uh, provide make hybridized orbitals. We cannot mix up two different orbitals of two different shells. For example, we cannot mix up 1s and 2s because the energy difference between them is very high, due to which we cannot hybridize them, mix them. On the other side, 2s, 2px, 2py, 2pz are similar orbitals of a same orbit, due to which the energy difference is slightly present. So the energy difference is quite low, due to which we can easily hybridize them, mix up them. In that case, we can easily hybridize them, mix up them. So in that case, hybridization of 1s 2s is not possible. If we are hybridizing 2s and 2px, then it's possible. How we are going to do that? We are going to do that in such a manner that here, when heat of reaction is provided, what will happen? 2s is having how many electrons? 2 electrons, due to which 2px is having 1 electrons, 2py is having 1 electron, 2s is having 2 electrons. But as the heat of reaction is provided, 2s will gain the heat of reaction, due to which the heat of reaction gained by 2s will cause the energy level of 2s, 2px and 2py to become same. 2s will have the same energy level as 2p, due to which both of the energy level will be same, both will become degenerate orbitals, and according to Hund's rule, degenerate orbitals have their electron filling one by one, then by pairing. So in that case, as it is one by one, first there will be one electron in 2s, 2px was already having one, 2py is already having one, and 2pz will gain the other electron, due to which the valency of carbon will become as 4. This was our rule. This is the actual valency of carbon, which was not uh, explained by electronic configuration by Hund's, according to which the valency was divalent. So in that case, this is how the valency is made. Apart from which, when it comes to the types of the shapes, it also gives the shape or geometry of different orbitals. Geometry of different orbitals. Now, carbon, in the case of carbon, there is the presence. In the case of carbon, there is the presence of 4 orbitals. Now, in the case of carbon, there is a presence of 4 hybrid orbitals. Now, these hybrid orbitals are formed in such a manner that here, when the heat of reaction is gained, all of these have equal amount of numbers. All of these are having one electron, due to which the orbital will not retain its original status. It will become a hybrid orbital. That hybrid orbital will move in such a manner that 2s combines with 2p, 2s becomes the same as 2px, 2py, 2pz, due to which there is the formation of a new orbital which is known as sp3 orbital, which is a hybrid orbital. Now there is not one hybrid orbital, there are the hybrid orbital as the number of orbitals were combined. As there are 4 orbitals were combined, there are 4 sp3 orbitals. Now 2s replaced by sp3 orbital, sp2 2pq, 2px replaced by spq, 2py replaced by sp3, while 2pz also replaced by sp3. These are the orbitals, and this is how this is sp3 orbit is. In this type of orbital, there are 3 p orbitals and 1 s orbital. This type of orbital is known as sp3 orbit hybrid orbital, and this is sp3 hybridization. When it comes to beryllium, beryllium is having a similar structure. First, let us discuss boron. So here, boron is having the same case. Here, 1s, 2s, 2s, 2px. Now, 1s is having 2 electrons, 2s having 2 electrons, 2px is having 1 electron. Now, in this case, how will it happen? The the heat of reaction will be provided, and 2py will gain one of the electron of 2s, due to which it will become as 2s1, 2px1, 2py1. But these will not retain their identity, which means here they will not retain their identity. They will become as degenerate orbitals, and thus they will become hybrid orbitals. And that kind of hybrid orbitals will be sp2 hybrid orbital, because there are two p orbitals, one s orbital combined together. As there are 3 suborbitals combined together in order to form a hybrid orbital, there are 3 hybrid orbitals. So instead of 2s, there will be sp2. Instead of 2px, there will be sp2. Instead of 2py, there will be sp2. In that case, there are sp2, sp2, sp2 orbitals, and this type of orbital is sp2 hybrid orbital, and this process is known as sp2 hybridization. Apart from which, 2p hybrid orbital. This 2p hybrid orbital is found in beryllium in such a manner that this is beryllium, beryllium 1s, 2s. 1s to 2s2 is a valency, but as it will gain heat of reaction, it will have its electron move into 2px, to which the electron will become 2px1, 2s1. This is the excited state of beryllium. At the excited state, it will then turn into a hybrid orbital with here 1s, here 2s and 2px will have collectively their hybrid orbitals to be named as sp hybrid orbitals. These would be named as sp hybrid orbitals. There will be sp1, there will be sp1, and as there are two orbitals combined, so there will be two sp. Now when it comes to their shape is determined in such a manner that here sp cube is having four orbitals, 3p 1s, so the ratio is 1 ratio 3, and sp square having ratio 1 ratio 2, and sp having 1 ratio 1. Now in this case, uh, total ratio is equal to 4, which means there are 4 orbitals, and these 4 orbitals are arranged in a tetrahedral manner. 1, 2, 3, 4. This is a tetrahedral manner in which they are arranged, and the angle between them is 109.5. Angle to be discussed as 109.5. Now there is another structure of sp2. Sp2 is having ratio 1 ratio 2 and total ratio is 3, which means 3 orbitals are there, so they will be arranged in a trigonal manner. 1, 2, 3. This is a trigonal manner, and as this is a trigonal manner, this the angle between them will be 120, or they will be directed towards the corner of an equilateral triangle. Apart from which, third, there is sp. Sp is having only two orbitals. These two orbitals will be arranged linearly in such a manner that this would be the linear structure, and the angle between them will be 180. Angle between them will be 180, due to which this would be the linear structure. Now, in this case, beryllium is having the sp3 hybrid orbital, which is having its angle as 180. Boron having its sp2 hybrid orbital, which is having its angle as 120, and carbon and nitrogen are having carbon, nitrogen, oxygen, fluorine are having their hybrid orbitals as sp3, due to which the angle is 109.5. Also, there are some exceptions which will be discussed in the next video, after which we are having a question that is hydrogen having hybrid orbitals? Answer is no, because in hydrogen there is only one electron, and that is making one atomic orbital, s orbital, due to which there is pure s character, due to which there is no mixing up of orbitals. As there is no mixing up of orbitals, there is no formation of hybrid orbitals. Next, when it comes to a few things we are going to discuss in our next video. Hopefully we'll meet again in another one.